Hello everyone, this is Dr. Lennon, and today we're going to look at Unit 1B, which is propositions and truth values. So this is where we start to get into statements and whether they're true or false, logically, and how they interact with each other via conjunctions and also implications. So let's go ahead and get started and go through some of the basic definitions. Is this view usually better? Yeah. Okay, so a proposition is something that makes a claim, and you can decide whether or not it's true or false, and it has to have the structure of a sentence. Pretty straightforward. So a proposition has two possible values, true or false. If it's a statement where that thing can't be verified, then that's another way to check that it's not a proposition. And a truth table is something we use where basically we'll just have the different statements and other things that we'll want to test the values on. So we'll look at some definitions about how those things interact and some examples before long. So the negation of a proposition is another proposition that makes the opposite claim. So this thing is going to have the opposite value. So if you have a proposition that's true, the negation of that proposition is going to be false. And vice versa. If you have a proposition that's false, its negation will be true. So yeah, there's a basic truth table, for example. We have P. If proposition P is true, then the negation, not P, is false. And if the proposition P is false, then not P, the proposition is true. So they've got the symbol down here. Sometimes instead of writing not P, you'll see the symbol, the tilde. So let me see, let me write that down. So the negation of, so notation. So the negation of P that is not P is denoted by either tilde P, or sometimes in other books I've seen where they just have this line, this like kind of sideways L P. So that's this book, it looks like they're just going to use tilde P, but I've also seen this. So back to the PowerPoint. And again, the negation has the opposite truth value. So if P is true, not P is false. If P is false, not P is true. Pretty straightforward. So find the negation of the proposition. It's usually pretty easy. Something as simple as this. Once we start introducing quantifiers, it'll get a little more complicated, but there's a straightforward way to go ahead and do that. So Amanda is the fastest runner on the team, right? It's negation. If the negation is false, is Amanda really the fastest runner on the team? So we just want to write a statement that we know will have the opposite truth value. So Amanda is the fastest runner on the team. Amanda is not the fastest runner on the team. That would be the negation. So if Amanda is really the fastest runner on the team, the negation, Amanda is not the fastest runner on the team. So it says if the negation is false, so that would make the original statement true. So that would make Amanda the fastest runner on the team. So the negation, Amanda is not the fastest runner on the team, as we said. If the negation is false, the original statement must be true because they have to have opposite truth values. Okay, the double negation. So these kind of things happen almost accidentally. Maybe it's the way we speak. But the double negation is just going to have the same truth value as the original proposition. We could check this pretty quickly. So a double negation is basically, if we want to go through the truth table, we would have P, we would have not P, and then we would have not P. So there's only two cases. Either P is true, in which case not P has the opposite value, false. And if you think about it, you could kind of put parentheses around not P. So if not P is false, then the negation of not P would again be true. It just, it reverts the truth value. Then if the proposition was false, not P would be true, which would make not P false. So notice P and the double negation of P have the same truth value. So that means the statement and the double negation are actually equivalent. Again, there's the truth table that we just wrote down. Let's look at this example. Really, the italics is the only thing we really care about, but let's see. After reviewing data showing an association between low-level radiation cancer among older workers at Oak Ridge, a health scientist from UNC Chapel Hill was asked about the possibility of a similar association amongst younger workers at another national laboratory. He was quoted saying, "My opinion is that it's unlikely there is no association." So, if this is his opinion, this is what he thinks is true. Notice it's a double negation because there's the word unlikely and also no. So the equivalent statement would be saying his opinion is it's likely there is an association. So if you remove both of those negations, that would be the equivalent statement. So does the scientist think there's an association between low-level radiation and cancer among younger workers? The answer would be yes, because the double negation would be equivalent to the statement they're asking the question about. Yeah, so as we see there, both those things happen, and it is equivalent to the double negation. So that is exactly the same as the original statement that they're asking a question about. So let's go ahead and look at the next example. Oh, so another just statement that the double negation is equivalent to the original statement. Okay, so now we start talking about connectors, and the three that we're going to discuss today are and, or, and if then. We have to be a little bit careful about or because sometimes the way we use or in English is different than we use it in logic. So we'll talk about that in a moment. But yeah. So a lot of times we'll have these conjunctions in sentences. So and or conjunctions, and if and then is known as an implication. So these are two statements, and we can look at their interaction. So obviously just pairing the two statements using and the word or is how we do that in sentence form. If then, we would say, if I won the game, then it was fun. Or you could say, if it was fun, then I won the game. You could do it in either order. P implies Q or Q implies P. So, yeah, okay, so as mentioned before, we have this, the conjunction. So here's how the truth table works. So the only way an and statement is going to be true are if both propositions in the and statement are true together. So if P is true and Q is true, then P and Q are true. If either of the two statements, one of the statements is false or both of the statements are false, then that conjunction P and Q will also be false. They have this symbol. So the notation for the and or are as follows. More notation. So P and Q can be written P and then this kind of upside down capital V. And P, I'll just jump ahead now, P or Q can be written P or Q like this, and then we can do the implication as well. P implies Q, or you could also say if P then Q. So maybe since these are the sentence versions of the statements, I'll put them in quotes. just to note that we have 2 here at the bottom. So this can be written P and then arrow Q. You can also do the reverse implication where the converse Q implies P, or if Q then P, and we'll investigate those truth values in those sentences in a bit. Okay, so that's how AND works. If they're both true, P and Q is true. If any part is false, then they're both false. So if we look at these, the capital of France is Paris. That part of the statement is true, and Antarctica is cold. That part of the statement is true. So since the first part, the capital of France is Paris, is true, and the second part, Antarctica is cold, is true, then that means that this statement A is also true. If we look at B, the capital of France is Paris. That's true. But the second part, the capital of America is Madrid, is false, because we know the capital of America is Washington, D.C. So since that part is false, then the entire statement will also be false. So yeah, as we see the solution here, both propositions are true, so their conjunction is also true. And then for the second one, since the second part is false, the entire statement is false. Okay, so we also have or, and this is, I think, talking about what I mentioned before. In English, oftentimes will mean exclusive or, meaning either one or the other. But when we're talking about or in logic, we typically mean what's known as inclusive or. So either one or the other or both. Yeah, so inclusive or means either or both. So you're going to have to train your brain when you're using this class to think in terms of inclusive or, if you typically think of or meaning exclusive or, one or the other, but not both. So for this class, when we say or, logically, we mean the inclusive or. Yeah. So in logic, assume or is inclusive. Okay, so yeah, so the or statement that we're going to talk about is also known as the disjunction. So the only way this is true. So if either statement or both is true, so we only need one part to be true. If both parts are true, it's also true. The only way P or Q is going to be false is if both P and Q are false. So we see the truth table here. We've got now 3 trues and then false. So true or true is true, true or false is true, false or true is true. The only way we get a false disjunction is if we have false or false. And again, the symbol is the regular looking kind of V. Okay, so let's think about the statement. Airplanes can fly or cows can read. Well, the first part is true, so we know since it's an or statement, the whole thing's going to be true. The second part, cows can read, is false, but that doesn't matter. We only need one part to be true. One part or the other or both. So as we see, the first proposition is true, second's false. Okay, so again, it just takes a little practice going through these statements, which we'll see on the homework. So if P then Q, this is known as a conditional proposition or an implication. I tend to use implication, I think. It's true unless P is true and Q is false. Okay, so the way it's true, basically, a true statement can only imply a true statement. But if your assumption is false, then anything you say about that can be true. So the only way you get a false implication is if you have a true thing implying a false thing. So we'll look at the truth table below here. So again, we have 3 trues in the conditional, and the only way you can get a false thing is by taking a true hypothesis and implying a false consequent. So true implies true is true, true implies false is false, false implies true is true, and false implies false is true. Yeah, okay, and I was using it already. The first thing, the if part, is the hypothesis, and the second part, the thing that follows the then, is known as the conclusion. There's other ways of saying these. it usually happens when you're in a more math environment, talking about theorems and stuff. But if you forget, you can remember that these things are often said. So the things on the left here, these are all if P then Q type statements. P is sufficient for Q, P leads to Q, P implies Q. So I'll say P implies Q a lot. I'll try to stay away from the sufficient and necessary terminology because I think it's probably a little confusing, but that is used as well. Okay, so now we have the these ways, which are also equivalent. Q is necessary for P, Q if P. It's kind of like backwards. If P, then Q, Q if P. It's understood, and then Q whenever P. So typically I'll try to stick to P implies Q, or if P, then Q, when I can. But if you come across the other terminology and you're not sure, just Google it. Okay, so variations on the conditional. We have the two main ones are the converse and the contrapositive. So so the converse. So consider the implication P implies Q. Are they using a single arrow or a double arrow? I think in logic they use a single arrow a lot. P implies Q. So why don't I switch that in my previous thing as well? A lot of times in math we'll use this double arrow, but in logic specifically they'll use like single arrows. So the converse of the statement is Q implies P. And the contrapositive of the statement is not Q. They use tilde. So not Q implies not P. Let's investigate the truth tables real quick to understand what's going on here. So if we have, so let's just remember, if you have P and Q, let's remember what we did for P implies Q, and then we'll try to think about how we can get that to the reverse for Q implies P. So if we have P being true and Q being true, P implies Q is also true. If you have P being true and Q being false, this is the case where the implication is false. And then if your hypothesis is false, anything you say about it is true. So this was the truth table we saw for P implies Q. So if we add a column and do the reverse, Q implies P, our hypothesis is now Q. So in this case, you have a true hypothesis, Q, implying a true consequent, P, so, or conclusion, P, so this would be true. But now let's look what's going on. So if Q is false, then we know anything we say about it is true. So we get true for this one. If Q is true and P is false, a true statement cannot imply a false one. So this one turns out to be false. And again, in the last row, Q would be false, implying a false P, but your hypothesis is Q, so that's going to make a false statement. So notice that the truth tables for P implies Q and Q implies P do not match up. So they are not logically equivalent. So note that. A statement and its converse are not logically equivalent. So that's important to note. The two big takeaways from this are going to be a converse and its statement are not true. So a lot of times people, when they're thinking too fast, are going to be that. And then we'll see what the contrapositive, it's actually going to turn out to be the same as the original statement. So let's do another truth table. So if we have P, Q, we know how P implies Q goes from above, but let's see how many. It kind of depends how many you want to do in terms of columns. So we could do not P, we could do not Q, and then we could try to do the contrapositive. So not Q, and then we could have our contrapositive, not Q, implies not P. So again, let's go through just the regular. So if P is true, not P is false. If P is true, not P is false. If P is false, not P is true. If P is false, not P is true. Then go through the Q statements. So if Q is true, not Q is false. If Q is false, not Q is true. If Q is true, not Q is false. And if Q is false, not Q is true. I'm just keeping the same order as I did in the above for the converse truth table. Okay, so now let's look at the implications. So not Q false, we'd be looking at false implies not P false. So that would be true. So not Q true implying false, that would be false. True cannot imply false. False cannot imply true. Sure, that's true. And true, will that imply true? Yes, it will. So notice the truth table with the same order for P and Q. P implies Q is true, false, true, true. And not Q implies not P is true, false, true, true. So note that these are logically equivalent. We get the same values using the same order of P and Q for P implies Q as we do for not Q implies not P. So note that the statement and its converse, and its contrapositive, excuse me. This is known as the contrapositive. Not Q implies not P. This one was not logically equivalent, but this one is. So let's see what kind of examples we have. So yeah, the two main takeaways: a statement is not the same as its converse, but a statement is identical to its contrapositive in terms of truth values. So if it's raining, I bring an umbrella to work. If I bring an umbrella to work, it's raining. So clearly you can see why, if it's raining, you would bring an umbrella, but you might bring an umbrella because you think it's going to rain, but maybe it ends up not raining. So you can just kind of see by example why the converse and the conditional would not be the same. They include the inverse as well. Typically, the converse and the contrapositive are the most important. These other ones are not as important to focus on. They have them. If not P, then not Q. But in terms of the statement, the two ones we typically think about are the converse. People often assume that that's logically equivalent, which is not, and then the contrapositive. Not P implies not Q, or not Q implies not P. Yeah, so here they did all of it as one big truth table, and you'll see if P then Q is not the same as the converse, but it is the same as the contrapositive, as we've already worked out. Okay, so let's look at this example. Consider a statement: if a creature is a whale, then it's a mammal. So write the converse, inverse, and contrapositive. Let's just focus on the converse and contrapositive. So the converse would just be the reverse order. If a creature is a mammal, then it is a whale. So we know the statement here is true, so the converse, it turns out to be not true in this case. right? So if a creature is a mammal, then it is a whale. This statement is false, right? Clearly there are mammals that are not whales, human beings, for example. The inverse, this is just if not P, then not Q. If a creature is not a whale, then it's not a mammal. Also false, right? Dogs are not whales, but they're mammals. And then the contrapositive, if not Q, then not P. If a creature is not a mammal, then it's not a whale. So that's certainly true. Yeah, so again, the original proposition and its contrapositive have the same truth values and are logically equivalent. All right, so that is the end of this. So that's it. So I also have the homework assigned for this section, which I'll make a short video about as well.